I'm going to show you 2 more problems and then give you a quick review, and we should be done with chapter 15. So here we are given a gaseous chemical reaction with a Kp provided and all of the concentration in ATM. Those are the partial pressures, of course, that are related to the concentrations. And before we can set up our ice table, we need to figure out which way this equilibrium shifts. So we set up Qp and just plug in the concentrations that are provided. So we have 0.1 ATM squared, right? We have 2 moles of the product divided by 0.100 times 0.100, because both of those concentrations of the reactants are the same. And so this is going to be 1, which means the equilibrium is going to shift to the right. This is products over reactants. 81 is larger too, so we need to increase the products and decrease the reactants. So that's how you also can think about which way the equilibrium will shift. This makes it a little easier. I already have the numbers. It's cleaner, so I know this is going to go down by a factor of x. Cl2 is going to go down by a factor of x, and our product's going to go up by 2x. I'll bring it all down to equilibrium. 0.100 minus x, 0.100 minus x, and 0.100 plus 2x. Those are my equilibrium concentrations. Now I need to solve for x. I'll plug it into the equilibrium expression. I'm going to go ahead and replace Kp with an actual number. So it's 81.9 equals 0.100 plus 2x squared, and then it is 0.100 minus x times 0.100 minus x. This is the same, so I can take the square root out of both sides. So I end up with this expression. I will multiply both sides by 0.100 minus x to bring this over to the left. That's the first thing I'm going to do. I'm also going to go ahead and take the square root out of 81, which is 9.08, so it's 9.05 times 0.100, and then minus 9.05 times x. That's going to be equal to 0.100 plus 2x. So the next 2 operations I'm going to do is I'm going to subtract 0.100 and then add. So I'm going to bring this over to the right, the 9.05x. So what ends up happening here is these 2 together make 0.905, and then if I subtract 0.1 from it, I get 0.805. So this is going to be 0.805 equal to, and I got rid of this. I have 2x. I'm going to add 9. So I'm going to add 2x plus 9.05x, which is 11.05x. And if I solve for x, x is going to be equal to 0.805 minus 11.05, which equals 0.0729 ATM. And that's x, so we still need to subtract that from our initial concentrations to get the concentrations at equilibrium. And I have it all written down here. Here's the whole problem solved, your algebra, and then here I put x in and calculated the concentrations or the partial pressures of the reactants and the products. And as always, if you want to check your math, you can plug that into your equilibrium equation and you should end up with the same value for Kp, because this is all done at the same temperature. So let's work one more, and this one is, you have to always pay attention, right? So here I am giving you a reaction. I'm going to give you a Kc, and instead of giving you concentrations and molarity, I give you the number of moles and I give you the volume. So there's just one little extra step that you need to perform, and that is to calculate the molarity, and that's shown here. All right, so all we have here is H2S, and we don't have any product, so we know it's going to shift to the right, and so this then gets put into our ice table instead of that. Now if you accidentally put moles there and you do everything correctly, I'll just take a couple points off, but you should always pay attention to these kinds of details and read your questions carefully. So now let's work this problem. We know it's going to shift to the right, so this will go down by 2x, this will go up by 2x, and this will go up by x. So we have 0.0250 minus 2x, and this is going to be 2x and x. If I plug that into our equilibrium expression, I'm just going to write Kc and not the number. I'll get this set up for you, and then you can solve the rest. So here we now have 2x squared plus x divided by 0.0250 minus 2x, and that's also squared. Alright, so this looks like it might get a little bit more complicated, because once you multiply this out, you get 4x cubed. Now we have a cube root, and that could make things just more complicated. But we're going to use a simplification or a little trick, and it doesn't always work, but this will become important. We are going to argue that Kc is very small, right? 10 to the minus 7. What that means is the equilibrium lies very much to the left. So x is going to be really, really small, right? This is going to shift by just a little bit. And if it shifts by if x is less than 5% of the initial concentration, then we can just assume that x is so much smaller than 0.025. So we can just get rid of that. But we have to, then when we solve for x, we have to take x and we divide it by the initial concentration, 0.025, to get a percentage. And if that percentage is less than 5, we are okay. If not, we have to use some more complicated algebra. But so this turns into 0.0250 minus 0, so that stays there, and so it makes it a lot easier to solve. And I have it, I'm not going to do it. Here's that assumption, here's the rest of your algebra, and so you end up x being 2.97 times 10 to the minus 4, which is pretty small. And here's your little test here. You divide that x by the initial concentration of H2S times 100, and you get 1.19. So you can this assumption is okay. So here's a good one for you to practice. Again, it's the same reaction. You are given liters and you are given moles. So now you are given a very small concentration of H2S, and so you are, the smaller that gets, the more you risk that x is not going to be smaller than 5%, right? Because it's going to be the same setup and you have a different value here. But again, this is your problem to solve, not mine, so I've given away too much already. This is the final slide. Just going to review Le Chatelier's principle, which is the way you can predict upon manipulating your solution or your equilibrium which way it will shift, or if the products are going to increase in concentrations of the reactants. It's a very simple concept. You're looking at adding CO2 in this first one, right? So what effect has having CO2 to the reaction mixture? Take note that it's the only gas in this mixture here, so when you add a product, it's going to shift to the left, and so that's all it's asking. But when you add calcium carbonate, it is not going to affect this equilibrium at all, because calcium carbonate is a solid, and it is there in abundance, so that means the concentration doesn't change, so there's no effect in this case. So for the next one, I have to explain a little bit more to you. What is the effect of decreasing the volume of a reaction mixture and increasing the volume of the reaction mixture? Okay, so if you have gases as your product, and so there are 0 moles of gases here, and there are 3 moles here of gases. And so if you have 2 moles and 2 moles, you have no change in volume. But if you're going from 0 to 3, you are going to see an increase in volume because you're producing a gas. But let's use a different example here. Let's say we have 1 mole of gas on the reactant side and 2 moles on the product side. If we have exactly 1 mole of an ideal gas at SDP, it's going to occupy 22.4 liters. And if you're producing 2 moles, you're going to increase the volume, right? You're going to double the volume. Now, if you're increasing the volume even more, you're going to shift this to the right even more. If you're decreasing it, you're going to shift it to the left. You can also think of it as pressure. If you increase the pressure, it's going to shift to the left in this case. And if you're decreasing the pressure, it's going to expand. It's going to shift to the right. So that's one way to look at it. So in this case, it's the same scenario. We have 3 more moles on the right than we do on the left. You could have, of course, something where you have 3 moles on the left and 1 mole, fewer moles on the right. Then it would, if you are increasing the volume, would shift to the left. If you're increasing the pressure, it would shift to the right. So, what is the effect of decreasing the volume on this reaction? Decreasing the volume is going to shift it to the left. Increasing the volume is going to shift it to the right. And finally, the following reaction is endothermic, which means you have to add heat as a reactant. It just makes it easier because it acts just like a reactant in this case. If it's exothermic, it's a product. So what is the effect of increasing the temperature? So if you increase the temperature, it means you are putting in more heat. You are going to shift it to the right. All right? So that's like you're adding a reactant. And if you're decreasing the temperature, it's like you're taking out heat, and you are going to shift it to the left. All right. That was fun. I'll see you later.